Good day and Assalamualaikum. My name is Hazimi Ismail from University Technology Mara, Penang branch. This is a video presentation of my research titled Effect of Cavity Volume on Cooling Performance of Synthetic Jet Device. Every electronic device will fail if it gets too hot during a process. If heat doesn't release out of the device very well, it will burn or catch fire. Even if the temperature isn't high enough to start a fire or melt a device, it could still fail if it continues to rise. Modern electronic devices must use the right heat transfer technology to get rid of heat generated inside as quickly and efficiently as possible so that components' temperature stay within safe operating range. Because of this, a wide range of cooling technologies have been utilized to remove heat from electronic devices. These technologies include heat pipes, liquid cooling, a vapor chamber, and synthetic jets. When heat pipes are used to cool an electronic device, they can help move heat from its source to a place where it can be released. This lowers the thermal resistance that the heat has to overcome as it moves. A heat exchanger that is cooled by liquid is built into a liquid cool system's heat source to remove heat and lower the air temperature. Vapor chambers are often used to cool electronics because they allow for more even heat flow and better heat sink dissipation. Synthetic jets have three main parts: the orifice, the chamber, and the oscillating driver. These basic parts of a synthetic jet are commonly used. The oscillating driver is a key part of the synthetic jet because it controls how strong and how often the jet moves according to H. Elliott and others. As stated by C. Lee and others, the oscillation of the membrane induces the flow of fluid into and out of the cavity via the orifice. Under specific operation circumstances, when the diaphragm undergoes a change in direction and fails to generate a jet, the fluid that was expelled is promptly retracted back into the cavity. Nevertheless, under ideal conditions of amplitude and frequency, the fluid that is expelled from the orifice experiences separation at the outer edge. The functionality of a synthetic jet relies on the injection and expulsion of high-velocity working fluid via a singular orifice. Synthetic jet exhibit a net mass flux of zero due to the expulsion and intake of high-velocity working fluid through a solitary aperture. According to Seeley and others, a synthetic jet is a device that generates a flow with no net mass flux, but is capable of producing momentum in the direction of the jet. Figure 2 illustrates the ejection and suction process of a synthetic jet apparatus. Synthetic jets have demonstrated superior suitability for cooling applications at the package and heat sink levels compared to other existing methods, owing to their capacity to direct airflow along heated surface in confined environment and induce small-scale mixing as mentioned by Shabani. In contrast to traditional fans, synthetic jets exhibit several advantageous characteristics, including the reduced noise levels, decreased power consumption, a versatile physical design, enhanced reliability, simplified miniaturization, and fewer falling concerns. The oscillating driver is critical in the synthetic jet because it controls the frequency and strength of the jet. Motor-driven pistons, piezoelectric diaphragms, and acoustic excitation are all common types of oscillating diaphragms. Accordingly to M. Dahlan and others. It implies that the type of device used to set the fluid in motion, as an example of loudspeaker, piezoelectric transducer, and so on, is more important in this regard than the arrangement of fins in the cavity. When compared to the greater significance of device types, the impact of fins on the efficiency of synthetic jet actuators is relatively insignificant, according to ICAES23 and others. A recent study on the effects of thermal, flow, and acoustic characteristics in different geometry of a loudspeaker-driven synthetic jet discovered that the best cooling performance is found at the resonance frequency, but the number of orifices also affects overall performance. Despite numerous studies, a study focusing on the effect of air volume at different distances on thermal cooling pumping jet devices has gone unnoticed. As a result, this research would look into the effects of volume cavities at different frequencies in cooling applications. The temperature and velocity of each sweat volume would then be determined using a synthetic jet with varying sweat volumes. The process will be completed by determining the coefficient of heat transfer. 3 experiments were carried out in this study, one on heater characteristics, one on varying the distance between the nozzles and the heated surface temperature, and finally on varying the frequency of fluid velocity. It used in the heater characteristics experiment to determine the relationship between heater power and temperature. The effect of temperature on the various distances between the nozzle and heated surface temperature was then investigated using a synthetic jet. Furthermore, at a distance of 50 mm from the nozzles to the heated surface temperature, the synthetic jet was tested at various frequencies ranging from 300 Hz to 700 Hz. 5 different cavity depth values will be used in the design of synthetic jet models throughout this study. Figure 3 depicts the fabrication of the synthetic jet actuator using 3D printing. Plastic is the material used to make the synthetic jet. And in the figure 3A and 3C show the diameters of orifice DO and diameter of cavity DC, which are fixed at 2 mm and 40 mm respectively. As shown in figure 3B, the value of depth cavity H range from 1 mm to 5 mm as shown in table 1. The data acquisition module DAQ and the thermocouple wire were used to measure and record the temperature of the heater in order to obtain 343.15 Kelvin, which is the common maximum temperature in electronic devices. The distance Z from the nozzle to the heated surface temperature of Model 5 was set as depicted in Figure 8. All distance were able to reduce the initial surface temperature of 343.15 Kelvin and maintain the temperature values after 400 seconds. Maximum temperature drop is found at 50 mm distance, from 343.15 Kelvin to 334.96 Kelvin, which is around 8.19 degrees Celsius. Figure 9 depicts the heat transfer coefficient at various distance for all models. At various distance, all models exhibit the same trend or results for the heat transfer coefficient, namely that as volume increases, the coefficient decreases. In all 5 models, the best transfer coefficient was found at a distance of 50 mm. Model 1 has the highest value among the 5 models, while Model 5 has the lowest value at all distance. The maximum heat transfer coefficient obtained at 50 mm in Model 1, which is 431.75 watt per meter square Kelvin. Figure 10 shows each synthetic jet models at a distance of 50 mm for each frequency. In comparison to other frequencies, 500 Hz was able to reduce maximum heat because it was fundamental to the resonance frequency, which fluctuates the maximum amplitude of the diaphragm. Figure 10 shows the velocity for all the synthetic jets models at various distances. The highest velocity of the static jet was produced by a short distance between the nozzle and the anemometer wire. The maximum air velocity was measured at 10 mm for each model of synthetic jet, while the minimum air velocity was measured at 70 mm. The highest air velocity of the synthetic jet model was 1.29 mm per second, and the lowest air velocity was 0.08 meter per second. As shown in Figure 12, the frequency of 500 Hz has the highest velocity for each model of synthetic jet. The lowest velocity value is 700 Hz. At higher driven frequency, a vortex flow tends to disperse and form secondary flow structures, resulting in decrease in velocity. As a result, the value of Model 5 at 500 Hz indicates that the maximum air velocity is 0.46 meter per second, while the minimum air velocity at 700 Hz is 0.01 meter per second, which is consistent with the previous research findings. The heat transfer coefficient and fluid velocity are calculated using frequencies ranging from 300 Hz to 700 Hz. The heat transfer coefficient and fluid air velocity are greatest at 500 Hz when compared to other frequencies. When oscillating diaphragm, the frequency reaches resonance, its amplitude reaches its maximum. When compared to the cavity with the largest volume, the synthetic jet cavity with the smallest volume produces the highest heat transfer coefficient. The effect of frequency on synthetic jet actuators produce a significantly greater cooling effect than the parameters of distance and volume. However, the distance between the static jet and the heater surface influence the value heat transfer coefficients, as it is discovered that a distance of 50 mm from the nozzle jet to the heated surface results in the highest heat transfer coefficient. When compared to other models, Model 1 produced the highest heat transfer coefficient overall distance. Meanwhile, Model 5 produced the lowest heat transfer coefficient when compared to the other models. In conclusion, the smaller cavity volume produced better cooling performance in the synthetic jet device than the larger cavity volume, as observed in this experiment. That's all I have to say. If you have any question, please email my corresponding email address, which can be found in the manuscript. Thank you very much and good day.